Yeah, hi there, everybody. Welcome to the Sonardyne Soundwaves podcast. We're here at Floating Offshore Wind 25 up in Aberdeen. And joining me, I've got Will Brindley from Apollo Engineering. And we'll be discussing a lot about the sector, but particularly around condition monitoring systems and how that affects the whole O&M strategy for a floating offshore wind farm. But first, I'd like to just introduce you, Will, and ask a bit about, maybe you just want to tell the audience a bit about what you do, what Apollo Engineering do, and a focus around floating offshore wind.
Sure, yeah. So at Apollo, we're consultants, so we do whatever our clients ask us. But our expertise is around marine systems, floating structures, cables, and mooring lines. That's where we put a lot of emphasis. And a lot of the work we've been doing is thinking about floating winds, how you design it. So we do lots of analysis of moorings and cable systems.
Yeah.
But we also look at how you can plan to inspect that system, how you install it, and the kind of things you need to think about while you maintain that system. So we've supported the Catapult on quite a number of studies, looking at maintenance of wind farms, installation, and what those studies look at is actually those aspects of costs are at least as expensive as the moorings and the cable systems combined.
Yeah.
So yeah, my expertise in Naval Architect, so floating structures and particularly the bendy bits, so cables and mooring lines.
Yeah, I think I've read both reports. I know you've got some upcoming reports as well. But I think that really sort of help shaping the industry, even though it's still in its very very early days. It's definitely hit some headwinds as the whole offshore wind sector. But yeah, maybe starting at that, like, first question, what's your general impression of the status that floating offshore wind finds itself in today? Have you have you got any sort of feelings on when it's going to start really happening?
I mean, for outsiders, it definitely feels like it's still ramping up. The sort of really detailed engineering, answering a really tricky question is still to come, or it's just starting. So there's a number of developers that we're working with, but the detail is still to come for sure. And that tells me, I think we might see some more delays on these projects. There might be some more surprises as we get more information from demonstrators. And I think we'd like to see those first, a more incremental increase from, the 3, 5, 10 turbines to the 50, 100 turbines. I think there's a room to sort of build in that more gradual increase of projects. So certainly in the next 5 years, we'd like to see those smaller projects ramp up, and then, mid to late 2030s, we get the really big projects.
So yesterday at the conference, they did like a fast track of projects, fast track session on project updates and phased approach. That was one of my takeaways, particularly for the Equinor Celtic Sea project. But really just smaller. I think they said something minimum of 300 megawatts, but that will be up to, I think it's 1.5 gigawatts.
Yeah.
So and I think that phased approach allows the developer to just test technologies. And obviously it's a dynamic environment. There's a lot going on there. So yeah, there's a lot of unknowns. But I suppose on that point, we know there's a hell of a lot of risk around the sector, but there are also learnings as well from other sectors, particularly oil and gas. But just firstly, how do you feel the demonstrators have gone generally, and potentially added value in terms of knowledge, industry knowledge, and reducing that risk profile of turbines floating at sea?
Yeah, I mean, obviously we're fortunate to have 4 or 5 major demonstrator projects now, with more going in the water. There's been more coming in the last few years. I think every time you do one of those demonstrator projects, there's a great deal to learn. And I think a lot of the emphasis has to be on, what went wrong as much as what went well.
Yeah.
Because you have to be able to learn these lessons when you're at a small scale, when you have time to make the engineering changes, make the design changes to make it work.
Yeah.
So obviously Trincarden, major component replacement. There's a lot that went wrong there in terms of it's a very expensive process to tow all the way to Rotterdam and back. But there's a lot that went right in terms of the learnings from that.
Yeah.
And especially doing that in-field replacement, that's a big win. So and you see that across all demonstrators. There's a lot of lessons learned. In some cases, I think it's a case of, what can we really reduce cost on, and what do we actually need to invest in, maybe increase costs to get it right and get that long-term performance. And then I think although these floating structures have all been around for like 50, 100 years in various guises, floating wind's quite different. The pressure to get that cost down and really refine what you need to refine is incredibly strong. And that's where the demonstrators come in.
Yeah, I think yeah, absolutely, I agree. And I think with you said about things going wrong, but that is part of the learning process. And I suppose doing it at demonstrator scale, that's has to be that way. We see, with SpaceX, and they talk about it's quite normal to have these challenges, rockets, whatever, blow up, and we don't see it to that magnitude here, but you need to go through that testing to ultimately deliver these units at scale and that are working effectively. That's good. But on that note as well, I know you've done some work with cross comparison against the oil and gas sector with data from the oil and gas sector. Can you give us any insight into some findings there and how that's helped you and Apollo Engineering generally, and then for the reports?
Yeah, I mean, absolutely. I mean, if you look at all especially the aspects of the floating structure, the mirroring lines, the cables, you have to pull from that wealth of experience from oil and gas. There's 30 years of experience. There's very good reasons to do things the way they're done, especially on the mirroring design side. And there's opportunities to steer things differently, for example, using synthetic ropes. But a lot of the issues around getting the details right in oil and gas is really important. So FPSOs, floating production units, they've been around for 30, 40 years. There's a vast amount of data on mirroring integrity issues, failures of mirroring lines, and really understanding why those happen, how you can monitor them, and how you can do it better is a really important part of that legacy. And that is now being translated into floating wind, but there are still some things we're learning. And it's exactly the same thing for cables as well. So we take that data set of
Risers and
umbilicals and the risers, power cables that use the oil and gas. You have that 20 years of data, and you can translate it to this nascent industry and start to learn about how you can protect those systems.
Yeah.
And yeah, some of the work we're doing in the catapult is really looking at how you take those lessons learned, you create a repair strategy, you create a monitoring strategy, and you make sure that you have a robust through life strategy for those systems.
Yeah. No, I think that's absolutely imperative. Just on the, just on that point, and obviously we just said we talk about condition monitoring systems, but first of all, what failure modes do you see pose the greatest sort of level of uncertainty threat to a wind farm? You mentioned about the mooring, corrosion and mooring integrity. But yeah, what would you say the big failure mode challenges?
Yeah, I mean, I guess for a turbine, unlike a lot of oil and gas structures, you have a big turbine on top, and that drives enormous loads. And what's quite unique about that is it drives enormous loads most of the time.
Yeah.
So your turbine is designed for a typical rated wind speed, maybe 12 meters per second. And at that wind speed, which you get about half the time, you attract the maximum loading on the structure, or near the maximum loading. So unlike, say, an FPSO, the maximum loading occurs when you have a 100-year storm. So you'll get your maximum loading maybe once a year.
Yeah.
On these turbines, you get that extreme loading half of the time.
Yeah. Okay. Yeah.
So that really changes how you have to design your structure, especially how you have to design the mirroring system. So all these structures and mirroring system, they're governed by fatigue requirements. And actually, that's a very different approach to structural design. You have to think about different things, get the details right with fatigue, because one small crack that can create a major collapse. So it's really understanding that change in loading, and that then opens opportunities for a company like Sonardyne, which can look at how do I monitor that fatigue, and how do I monitor things like wear as well. So things are moving, they're wearing against each other. Quite hard to calculate. So if you can monitor and measure then it's a way of really better understanding that structure.
Yeah, absolutely. It's so. Do you see the condition? I mean, it's an interest at Sonardyne, especially around the moorings and whether it's measuring load or angle of the mooring, anchors as well. That's also a critical bit, and also sort of dynamic cable. But do you see condition monitoring necessary for sort of all components given the outcome, or is it the outcomes, or there's different levels, I suppose, in criticality? Sort of. Yeah.
Yeah, absolutely. I mean, I guess what's unique about particularly a floating wind farm is you have 50, 100 cloned assets. You know, if we do it right, we do it at the right scale, the gigawatt scale. So that's very different from really anything else we've seen, where you have a single asset, single floating asset, you know, everyone's slightly different. You can use that opportunity that they're all cloned to take a sample.
Yeah.
Take a sample of mirroring lines, sample of bits of structure, sample of cables, and then infer what's happening to the rest of the field from that sample. So it allows you to get, you know, leverage maybe a 5-to-1 or a 10-to-1 more benefit from a single monitoring device.
Yeah.
Because everyone's similar. Not the same. You got difference in water depths, difference in different things.
There's different characteristics as well across. I mean, it's a big acreage here as well, isn't there? So you have to select, the turbines, specific turbines, and then narrow down to certain components. You're depending on, like I say, those wider characteristics.
Exactly. Yeah. But it does allow you to do things differently and get a lot more value out of the monitoring system. Yeah. And also more value out of engineering as well, because that engineering that you've done for one floating structure will apply to all of them. So there's a definite business case there to really invest in time to get it right.
Yeah, absolutely. On the business case, that's actually a good point, because I've got that noted down. Have you got any idea in sort of, say, mooring failure? And I think we have spoke about this, but the costs incurred, and you know, what are the sort of magnitude of like a single line mooring failure to a offshore wind farm at scale?
Yes, I mean, it's a difficult question to answer, because you have to sort of look 3 or 4 steps ahead in that chain of failure. The classic example is the Griffin FPSO or the Banff FPSO. These happened around 2010, big 1-year storm, and in both of those instances, you had about £500 million of damage.
Yeah,
most of that damage was from repair costs of the subsea infrastructure. So the structures drifted off position, mirroring lines broke. There wasn't a major oil release, but those subsea assets destroyed the undersea infrastructure.
Yeah.
So you could envision a similar kind of failure mode for floating wind. You have a chain breaks, something else happens to cause that turbine to drift, so you have more failures.
Further stress.
And at that point, you've got to really be concerned about major catastrophic costs and how to mitigate that.
Yeah.
So the chain that you're dragging behind that floating turbine is effectively acting like a wrecking ball. So you have to really think about what assets are in the way, what could happen. You know, I think we're still in the process of understanding that, really to understand risk. But some of the studies we've done, for example, for the catapult, have shown that actually there's quite small tweaks you can make to your mirroring design to really cut that risk down by a factor of 10.
Okay.
So one of them is addressing integrity.
Yeah.
So prevent a failure in the first place. Yes, obviously the best way of doing it.
Yeah.
But it's not easy because there's all these different failure modes. And often in mirroring systems, you fix one thing and then something else comes up.
Yeah.
So mirroring integrity, robust ropes, you're really focusing on fatigue. It's important. But you have to accept that just mirroring lines will fail at that kind of scale.
What degree of failures do you expect over the lifetime of a wind farm?
So, and again, if you look at this oil and gas statistics, you might expect it varies, but typically 1 or 2% per asset per year will fail a mirroring line.
Okay.
If you look at FPSOs, there's a lot of questions around whether that really scales up for a cloned array. It's more like all or nothing. But if you just take that 1 or 2%, you multiply it by 50 turbines, and that's basically a failure per year at the big array scale.
Okay.
So there could potentially be a lot of busy anchor handlers out there.
Is that a particular type of mooring though, whether it's chain or synthetic, or If you see that, is it?
I think the failure modes will be different. So we generally see ropes being more robust
Yeah,
if you can avoid them being cut.
yeah,
So most of these cutting edge floating wind turbine mooring designs, they're composed predominantly of rope, partly for performance and cost reasons, but also rope it doesn't really fatigue. If you get the design right, it doesn't corrode and it doesn't really wear. So you've got these three main failure modes in the oil and gas sector that you eliminate by using rope.
yeah. Okay.
But the weakness of rope is that it's sensitive to being cut. So
Yeah.
it doesn't take much, maybe a fishing trawler, maybe an errant anchor, maybe sabotage. Wouldn't take much to cut through that rope. And then you've got this potentially catastrophic scenario. So you have to manage that, but if you get it right, I think there's an opportunity to really improve mooring integrity, prevent failures.
Yeah, and just on that point as well. So I talk about a lot of, I personally, we talk about baseline measurements, but ultimately, when do you think that sort of monitoring of a turbine components should begin? Is it at that, like literally at point of manufacture and then tagged electronically and it moves into the system? You know, like that you can. I was talking to a chain maker or OEM yesterday, and they were saying that probably potentially is possible. You know, that you're taking an image of a mooring as built, or as it's built, but then you transfer as it transfers into this field, you can start to begin that monitoring process. So you really have a good understanding of change over time.
Yeah.
But yeah, what's your thoughts on that?
I mean, certainly like a lot of issues occur at manufacture, and I think as we scale up and we're not making 10 chains, we're making 1,000. Yeah, 1,000 kilometers of chain. That's a huge step up, and I think there's a lot more that could potentially slip through the nets, a lot more potential for complacency there. So really being hot on manufacturing quality, manufacturing oversight, and tracking what have I tested, what how are we actually following this quality process is important. I think you mentioned like benchline or
Baseline. So
baseline.
in the field, you'd have an asset as built, and then you take your baseline measurements, and then it gives you your sort of reference point, your digital twin, or whatever you want to call it, but your model to then measure the change over time. But I think it's fair to say, like you know, when the sort of from the manufacturing to the deployment of an asset, there's lots of different loads and potential failure modes during that process. So just to sort of get that, because the criticality of monitoring through the whole sort of life cycle. So but the baseline,
I mean, we see that baseline is really important, because if you have a data point in 5-10 years time, and you come in and inspected it and you don't know what you started with, then it's almost a useless data point. So it's so important that when you've installed that system, a really, really robust as-built survey. Could you measure chain diameters? So when you come back to measure them again, you have something to reference again. Because often we look at measuring chain, and actually the as-built diameter is somewhat different from the specification. It's often overbuilt. So when you measure in 5 years' time, you need something to compare to. That's just an example. But all of that benchmarking is really important to get value out of your data.
And I suppose listeners, like at the moment, they could think, well, that's a lot of data you need to acquire. But I think with automation and AI, but automation in terms of collection of the data, and we'll touch upon robotics in a while. But there is now we're starting to see a sort of step change in how we can acquire and manage data. So that should help.
I'm interested to see what kind of ideas Sonardyne have as well on how to make that efficient, how to go from an Excel spreadsheet or a Word document that has lots of data points in to something a little bit smarter, a little bit more usable.
Yeah,
I guess.
Yeah, absolutely. I was at a conference recently, and I think one of the sort of sticking points is, I won't say it's a problem, but sticking points is we've got a lot of great technology acquiring data, especially photogrammetry data and laser, and not just in the sort of asset and the wider area, sort of seabed and sub-bottom profiling. Problem is the technology is that good now that it poses, but it also acquires so much data. But now the problem is how we process that data, and AI it's potentially the answer to everything, but it's caught at the moment as a bit of a bottleneck. So I think that's with Sonardyne and some of the things we're looking at around automation. That's definitely something we're aware of. And
Yeah.
yeah,
I mean, that would seem like, I mean, I'm still on the fence about some areas of AI, but
Yeah.
that would seem to be a very good application of AI. If we have a very specific problem, which is essentially you've got terabytes of data that no human would want to go through, and you're able to sort of classify, help the AI, validate the AI, and then at that point you can really automate that and allow you to do it year on year at the hundreds of thousands of asset scale.
Yeah, I think absolutely the validation and the trust in the processing, the AI processing, that's critical. And I still, yeah, that's why you still require that human in the loop for sure.
Yeah.
Especially, but that's the thing, as the scale offshore increases, you know, the sort of requirements for power generation, we're also, and alongside these step change in technological in developments, it's all come at once. So it's just ensuring we take the right steps to sort of standardize and yeah, you ensure a right, we have a right procedure.
Yeah.
But yeah, just a little bit more, go into a bit more of a technical detail. I've got some sort of, I was thinking, you mentioned about fatigue being so critical. What's how might fatigue and wear on moorings evolve? Can you give us a bit of an insight over, say, a 30-year? Because these projects, I mean, they're talking 30 years. I've even heard 40-year, 50 years potentially in the Celtic Sea. But yeah, what's the main drivers of the fatigue, mooring fatigue?
Yes, I mean, there's the fatigue, wear, corrosion, they're sort of interlinked to some extent. So often and we've seen issues that are ultimately a fatigue crack or a fatigue failure. That fatigue is a cyclic issue. So basically you've got lots of tension cycles, sometimes bending cycles. Chain doesn't really like to be bent. If you have a lot of those over time, they accumulate, they create a crack, and then that crack will ultimately lose the strength of the chain and lead to failure.
Yeah, okay.
Same for sort of connectors, and any steel component sees fatigue. So you have that, but you also have corrosion, and those interact as well.
Yeah.
So if you've fatigue stress something in air or in a protected environment, that crack will go much more slowly than it would in a heavy corrosion environment.
Oh, okay.
So there's that element of it as well. And often what we see too is over 10, 20 years, you can get things like microbial corrosion, and that causes local liquid pits and extreme corrosion on a specific part of the chain. That acts as a stress raiser, which raises the fatigue crack, which then makes that happen more quickly. So there are sort of interactions with fatigue. And then I guess the other uncertainty is really, what is that whole system doing to load our chain? And does it match reality? Does it match our model?
Yeah. Okay.
So there's a lot of uncertainty there, and you can do analysis to your forever.
Yeah.
And you might still not get the right answer. Yeah. It's just realities and physics that you don't fully capture in that model.
Yeah. I've having worked some areas when I used to work offshore. Yeah, I mean, temperature as well as water temperature, pH levels, there's all those different factors, and they do change as well. So, but with corrosion, yeah, that's an area we're particularly interested in, and but as well as for sort of fatigue and load monitoring. But yeah, that's interesting really with the corrosion, how critical it is to understand the change or the build up of that. Yeah. So just going down to the sensing side of things. I mean, you've got sort of your GPS or GNSS helping measure excursion and the attitude or motion of the foundation. You've got environmental sensors cross-correlating that track that movement, the environmental forces on the structures itself. And then you've potentially got mooring sensors and dynamic cable sensors. But how do you see that sort of hard sensor technology informing the digital sort of twin, the digital representation model too? And how does that extrapolate?
Yes, I think there are demonstrators that are looking at how you can do this. Some technology has been trialed, but again, at the gigawatt scale, I think it's still to be worked out exactly how you do this. Our thinking is, again, as part of this catapult study, the way to do it is use the assets you'd already monitor anyway. So, very high accuracy GPS monitoring. So you have really robust position. And I guess the key thing for that is if you're going to use that for a mission critical thing, like monitoring mooring failure, monitoring turbine behavior, that has to be incredibly reliable. So you can't have signal dropouts. You have to have almost guaranteed quality signal the whole time. There's an analog for this in dynamic positioning. Where you have to have redundant sensors.
We get asked a lot of questions, particularly at the moment, about jamming and spoofing. So and if you're relying on the GPS or GNSS network, then that poses a problem. But sorry,
No, absolutely. I guess Sonardyne also have a lot of experience, so there's a lot to take from dynamic positioning, ensuring redundant sensors, and then applying that technology and approach to floating wind. And there are lots of ways to do it for floating wind. So good GPS, then you can monitor motion and acceleration. And if you monitor motion and acceleration for the short period, for example, where GPS might fall out, you at least know where you're going, so you can patch up that signal.
Give yourself a level of redundancy.
So that certainly gives you a level of redundancy. There are also other methods as well, which is like referencing a seabed point. So maybe you could do that at least on a few turbines. So if your GPS drops out, again, you use that sampling to sort of fill in the gaps. It costs money, but not at the kind of proportion that the risk level lies, really. So certainly having that redundant sensing was really important. And then I think we'd like to see that sort of meshed in with subsea sensors as well. But you say you got 300 mooring lines, 300 cables, 100 hulls. You don't want to censor all of those to death. Our experience is these sensors, they don't last forever. And there's quite a big overhead with installing, maintaining, and monitoring them.
And then there's cross-validation of other sensors as well. So you just have to be a bit careful on how much, how meaningful the data is. But
you get that balance. And I think we see sort of like the house in the turbine where you can keep it dry, keep those sensors for a long time, and then subsea have a sample, so have a limited number, maybe 10-20% of your assets.
That's
subsea censored, and then use that to fill in the gaps, validate, and ultimately go with the dry sensors.
I think where we see value with the hard sensing is we conducted the French Energy Marine trial with the dynamic cables, lazy wave, and we had it was shape sensing really. There was a few other participants with sort of through fiber optics, strain sensing. But I think what we sort of exemplified was it was quite straightforward position of the cable at different points, 6 different points. But it was just interesting. You see that real world effect, and that you mentioned before about modeling and coefficients, that you are able to sort of look at the tidal effect on the touchdown points, in real, and have that confidence that then that you can transfer that into your model. So
there's definitely no replacement to having a real sensor. It doesn't have to be on every cable, but if you have a good sample and you have confidence that actually my system's behaving as I expect. I've got a lot of marine growth. It's sagging heavier than I expect. Need to do something about that. I've got something that's different. And I think that's probably where the demonstrators come in. Got back to your previous question about let's over sensor those systems so we can learn as much as possible, and then maybe we can take a more lighter approach at the bigger scale.
I was going to ask as well about standardization though. Do you see the standardization coming into the sector for condition monitoring, data interfaces, sort of your alarm thresholds, do you see, across the OEM and sort of operators, do you see that happening? I know obviously yourselves, DN, but also the standards providers like DNV, they're thinking about it, but I haven't really seen anything around condition monitoring at the moment.
I think there's certainly a lack of standardization on what is required. I think like the likes of DNV would probably have a risk-based inspection strategy as a preferred option, or certainly an option, but they don't really dictate what that looks like, what systems you have to have in place, what level of redundancy you have to have in place, what level of monitoring. I think it's all to be worked out. I don't think you necessarily have to have this is, the specification for monitoring.
They're all different as well, aren't they? Different. Different technologies, different site characteristics.
If you talk about like a £4 billion investment, 50 assets, do you really need that to be the same as the next £4 billion investment with 60 assets? You know, like,
Yeah.
I think there's a room for each wind farm to do it slightly differently, but I think also there has to be some general consensus that, yes, we need this level of redundancy, we need to monitor this, and this is a value that we need to get from the data.
Yeah.
And I think that helps insurability as well.
Yeah.
Because ultimately the cost of these arrays is very largely driven by finance.
Yeah.
So if you can have more confidence that you understand how your asset behaves, that it's actually working as you expect, then that cost of finance is going to come down.
Confidence right across the sector, isn't it? Bankability, insurance, design. You know, the engineering sort of fundamentals. So yeah, it's
whether it's good news, yes, I know how my asset's behaving and it's going well, or I know how my asset's behaving and there's actually a problem, but I can go in and address it early. So there's, whether it's good news or bad news from that system, you can still get value from it in confidence building.
Yeah, absolutely. Okay, so sort of we've addressed a bit around the condition monitoring, but how do you see that at the moment? I think if you look at fixed wind, that the inspection campaigns are quite fixed, you know, routine. Whereas, how do you see the this data being able to inform on predictive maintenance and sort of trigger inspection campaigns? Do you see it changing? I did speak to a developer yesterday. We're talking around 5-year campaigns, but do you think as with this abundance of data, information that should be accessible, do you see that there's an opportunity to maybe change around it, and especially with the emergence of robotic systems?
Yeah, absolutely. I mean, robotics aside, I suppose if you have just a manual, remote operated vehicle campaign, having monitoring allows you to really focus in on fewer assets and get more value from what you are looking at. And so there's some things that remote monitoring will not tell you. It won't tell you whether you have a serious wear problem necessarily. It might not tell you have a serious corrosion problem, but you can use it to fill in some of the gaps and then focus your time on the failure modes and the things that will actually you can't detect from monitoring and you are concerned about. So I think we'd never see inspection being replaced. But we do see it being more focused than it currently is. Currently, a lot of FPSOs, you have like 100% visual inspection. You have a lot of ROV time, months of campaigns going down a mooring line and really not seeing very much, looking at a whole structure and not seeing very much. So to be able to sort of focus and make sure you get value from the time that you're in the water is very important. And that's a sort of ROV campaign. I guess be interested to see what your perspective is on autonomous inspection, remote inspection, whether it's a sort of autonomous vessel that's controlled from shore, or whether it's a completely autonomous system. I think that's where the big opportunity to do stuff at a tenth of the cost comes in.
Yeah, absolutely. I think it needs to be modelled properly, and we need to take into a lot of considerations. But yeah, it's definitely been spoke about. I mean, we talk about residency quite a lot, especially for oil and gas developments as well. Sort of with now the emergence of 6 degrees of freedom tetherless vehicles, and giving you that longer life residency in the field, that becomes an option. But also, though, you have to look at the balance out. How quickly can it conduct that campaign? So if it is resident, are you going to have something sitting on the seabed doing nothing so I think that blend of having maybe like you mentioned before, the autonomous vessel being able to transfer between sites with that capability, I think that offers strong opportunity. But yeah, it needs to be, you need to really go through the sort of logistics detail and I think for business case.
Fundamentally, having a sort of 70-meter long surface vessel with 100 people on board to pilot an ROV is madness. There has to be a better way of doing it. So having some level of autonomy, whether it's a resident vehicle or an autonomous vessel that just goes and does its thing, it gets data and then sends the data back to shore, there has to be a better way of doing these kind of routine inspections. I mean, certainly the surface assets are maintained by resident vessels effectively. You have almost a permanent SOV, Service Operation Vehicle.
But that's always going to be, because you still need people as well out there for nacelle, and sort of looking at the turbine.
You'll always need that. But we're looking at drone technology to complement some of that.
Yeah,
and see.
So reduce down the man hours.
Yeah.
So
you can see the sort of complementary system of a monitoring system that complements the underwater monitoring, which complements the inspection, and then that's also complemented by an autonomous inspection system that just goes around and does its thing. That's where you can get a lot of value, I think, from this, but also a lot of data to handle.
Yeah, absolutely. I think we've chatted for over half an hour now. So I think and we've landed where I wanted to, really, on that sort of looking down on the horizon, what technologies are going to help to sustain this sector, and ultimately keep turbines in operation, electrons moving. But yet I think we're done. I did have a question about AI and how you see that, just affecting the sector, how it can enable this sector. We did discuss it before, but I mean, I don't know if there's any, for the holistic O&M strategy. Do you see? Do you have a vision on how really that will be sort of critical, or is it just? Yeah, we're still finding out.
We're certainly looking at it a follow, but I think we're still finding out where the application is. And my feeling for AI is choose your problem wisely. I think there's some problems that the current generation of AI do well, and some of it that it doesn't really help. It adds more uncertainty.
Yeah.
So I think if you're looking at monitoring data, that would be a question about what you use for AI there. But I think it's certainly inspection footage, inspection data. I think that's probably a really good opportunity.
Yeah, so more in the inspection side as opposed to...
Yeah.
I think it will help with the monitoring processing, but I think that's probably further ahead. I think the inspection side of things, and that absolutely, that's what we're looking across at Sonardyne and across our Cavalier group, particularly with our sister company IBA. But ensuring that ultimately that understanding, detection of change, and that delivery to the client so they can act upon it is delivered sooner.
Yeah.
But no, I think we're done. Thanks a lot, Will.
Thanks, mate.
So thanks for listening, everybody, and catch us on the next podcast, Soundwaves podcast. Hopefully at another renewables event soon. But cheers.
Thank you.
Thanks very much.